Hey, just look around you for a second. Right now, the world is transforming in like a million different ways. You've got things cooking, growing, rusting, burning, and believe it or not, it's all governed by this kind of secret language. So today, we're going to crack that code, the code of chemical reactions. So what do these things have in common? A rusty old car, a cake rising in the oven, even the very air you're breathing right now. What's the connection? Well, it's the exact same fundamental process at work in all three, and that process is a chemical reaction. Okay, but how do you actually spot a chemical reaction out there, in the wild? Well, it's all about looking for the clues. And that's our first mission today. We're going to become chemical detectives.
So it turns out chemists look for 4 key clues, kind of like fingerprints at a crime scene. Let's break them down, one by one, shall we?
First up, you've got a change in temperature. Some reactions release so much energy as heat that you can literally feel it. Take quicklime and add it to water like you see here. That mixture gets hot. That's what we call an exothermic reaction. It's just a fancy way of saying it gives off heat. And it is a dead giveaway that a chemical change is underway. All right, next up, look for a change in color. This one's a classic. You pop a regular iron nail into this really vibrant blue copper sulfate solution, and then you just watch what happens. The blue starts to fade away, and the nail gets this kind of coppery brown coating on it. And that right there, that's your proof. New substances are being born. Clue number 3 is bubbles. You see, if you add some dilute sulfuric acid to zinc, the whole thing starts to fizz. And every single one of those little bubbles you're seeing in this flask, that's a tiny pocket of brand new hydrogen gas forming right there before your eyes. And for our final clue, we have a change of state. Now, this is really cool. You can mix 2 perfectly clear liquids like sodium sulfate and barium chloride, and suddenly a solid white substance just appears. It looks like it comes from nowhere. That stuff is called a precipitate, and it is an absolutely dramatic sign that a chemical reaction has taken place. All right, so now we know how to spot a reaction, but how do we actually talk about it or write it down? Well, chemists have this awesome secret code, a shorthand that makes everything super quick and easy. So let's learn the language. Can you imagine having to write that out every single time? It's accurate, sure, but wow, what a mouthful. It's pretty obvious scientists needed a better, faster way to communicate. So the first step toward that is something called a word equation. It's super straightforward. On the left, you have your starting ingredients, we call those the reactants. And on the right, you have your results, the products. And that little arrow in the middle, it just means yields or turns into. Simple, right? Nice and clean. But wait, we can go one step further. We can make it even shorter. What if we replace the words with their chemical symbols? Well, then you have the ultimate code. This is the universal language for reactions. Mg plus O2 yields MgO. That is how chemists all over the world speak.
But here's the thing. This code, as cool as it is, has a golden rule. It's a fundamental law that holds the entire thing together. And it's all about one thing: balance.
It's called the law of conservation of mass. And what it means is actually pretty simple. You can't just create or destroy atoms in a chemical reaction. You can only rearrange them. So whatever atoms you start with, you absolutely must end with. No exceptions. Period. So let's take a look at this equation for iron reacting with steam. Think of it like a skeletal equation, just a first draft. Now, take a close look. Does that seem right to you? Let's do a quick count of the atoms on each side and see what's going on. And yup, this table shows the problem plain as day. We start with 1 little iron atom on the left, but we end up with 3 on the right. We start with 1 oxygen atom, and it magically becomes 4? We have totally broken the golden rule. This equation is unbalanced. So the big question is, how do we fix it? Well, we use something called coefficients. Those are the big numbers we can write in front of the formulas. Let's walk through this together. Okay, first, let's tackle the oxygen. We've got 4 on the right, so we need 4 on the left. The only way to do that is to put a big 4 in front of the H2O. Now, of course, that messes up our hydrogen count. It gives us 8 hydrogens on the left. No problem. We just put a 4 in front of the H2O on the right to match it. Okay, almost there. Finally, we have 3 iron atoms on the right, so let's put a 3 in front of the Fe on the left. Now, let's do one last check. And look at that! Everything matches up perfectly. The law is satisfied.
All right, now that we've basically mastered the code, we can start to see the bigger picture. It turns out that most chemical reactions actually fit into a few common families or types. Let's start with two that are basically polar opposites. First, you have a combination reaction. That's where two or more things combine to form one single bigger thing. Think of it as A plus B gives you AB. Then you have the exact opposite, a decomposition reaction. That's where one big complex thing breaks down into simpler parts. So AB breaks apart into A and B. See? One builds up, the other breaks down. Next up, we have displacement reactions. And hey, remember our iron nail from earlier? Well, here's what was really happening on a chemical level. It turns out iron is just more reactive than copper. So it literally kicks out the copper from that blue solution and takes its place. It forms iron sulfate. And that leftover copper that got kicked out, that's the solid metal that coats the nail. Okay, so if one element can switch places, why not two? That brings us to double displacement reactions. The best way to think about this one is like couples on a dance floor just swapping partners. The sodium decides to pair up with the chlorine, and the barium pairs up with the sulfate. And very often, this partner swap is exactly what creates that solid precipitate we were talking about earlier. All right, for our final section, let's bring all this theory back into the real world. We're going to look at one specific type of reaction that genuinely affects your life every single day. It's a little thing called oxidation. And here's the simple way to think about it. If a substance gains oxygen during a reaction, we say it's been oxidized. If it loses oxygen, we say it's been reduced. They're basically two sides of the same coin, and you can't have one without the other. They always happen together. And believe me, oxidation is everywhere. You know when iron gets wet and sits out? It slowly gains oxygen, and what do you get? Rust. That's corrosion, and that slow chemical reaction causes billions, with a B, billions of dollars in damage to cars and bridges all over the world. But it also ruins our food. When the fats and oils in, say, a bag of potato chips get oxidized, they go rancid. That's what creates that awful, stale taste. And that is exactly why chip bags are flushed with nitrogen gas to push all the oxygen out and keep them fresh. So, there you have it. This secret language, well, it isn't so secret anymore, is it? It's the code that describes our entire world in motion, from a roaring fire to the quiet little fizz of an antacid tablet in a glass of water. So now that you have the decoder ring, my question for you is, what chemical reactions are you going to spot in your world today?